Hi, welcome to Physics 2211 Lab 4 on Oscillations. My name is Maria Jyotish, and let's get started. The purpose of this lab is to observe the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. Some fundamental physics principles and models we can see in this lab are Newton's second law of the momentum principle, which relates the net interaction between the system and its surroundings to the observed motion. The second fundamental principle we'll see in this lab is the first law of thermodynamics, or in other words the energy principle, which states energy is neither created nor destroyed, but it may transfer from one type to another. And for a brief preview, the two models observed in computation will show the slight impact of external forces causing the discrepancy between their data, and the change in total energy of the system oscillates around zero. Some physics ideas that we will use are Newton's second law and the energy principle as mentioned before, as well as potential energy, kinetic energy, and period of oscillation. We expand on the momentum principle to get the velocity and position update formulas. We find the kinetic and potential energy of various forces acting on the system like gravity and spring force, and apply the energy principle to observe the change in energy over a period of motion. mg delta y is the potential energy due to gravity, and 1/2 kf squared is the potential energy due to the spring. We use T is equal to 2 pi square root m over k to solve for the spring constant. Here is a video of our observed mass, the system being the spring, mass, and the earth, and there being no surroundings. This allows us to set the work done by surroundings to equal 0 and no heat exchange. For our initial conditions, based on the length of our video, we find delta T to be 0.095 seconds. The mass weighs 0.402 kilograms. Our initial position is negative 0.079 meters in the x direction, negative 0.654 meters in the y direction, and 0 meters in the z direction. Our initial velocity in all directions is 0 meters per second. Using our tracker data, we solve for period of oscillation by calculating the approximate time it takes for one oscillation. In our experiment, that was 1.638 seconds. Now using that value, we use the period of oscillation formula T is equal to 2 pi square root m over k to solve for k. We solve for this and get k to be 9.688. Next, I use GlowScript to create a computational model of the system. Up here, you can see the initial conditions, ball mass, position, velocity, and time matching our observational model. Next, I added the constants that we know and previously calculated like K. Then I added the potential energy formulas of the spring and gravity as well as the kinetic energy formula. Down in our loop, I calculate the net force based on the force done by gravity and the spring on the mass. Then I solve for S based on the updated L of the spring. Knowing S, I can calculate the energy change of the spring and then find the energy changes of gravity and find the change in kinetic energy to calculate the total change in energy of the system. Next, taking the observational and computational data, I used Excel to create a position versus time graph to compare the results. You can see here there is a slight discrepancy between the two datasets, most probably due to human error of incorrectly plotting data points on tracker. Or in our observational experiment, we may have lost energy in the system due to it not being in an ideal world. Some follow-up questions are, is the energy principle satisfied? In our situation, yes, because as indicated by the orange line, after one oscillation, the change in energy was always 0. Next, we are asked to estimate the period of oscillation using our x position data and y position data. The period of oscillation I found from the x data was 1.638 seconds, and from the y data it was 1.5004 seconds. The difference is most probably due to drag or air resistance acting on the system. Thank you for watching.